let's start with
Oops. OK, thank you very much. My talk will be about metal and dust with mosquitoes in the early universe and the transition from stardust to ISM ground dust, and the link of this with the JWST VXS that we observed. So that's a work with people in Marseille and in Japan, Massachusetts, and the SEARS team, and the PI is Steve Finkelstein. So let's start with the life cycle of dust. So this is a galaxy, for those who don't know. And, oh, you know? Oh, sorry. So you have dust, you have stars, you might have, and you certainly have an AGN in the center, and you have one star here. And if you decompose all of this, you will get what is called the life cycle of dust. Well, you have different life cycles, but this one is of dust. So let's start at some point. For instance, star formation. So you start forming stars. And these stars, of course, evolve depending on their mass, initial mass, into various things. And here we are interested in two types of stars, AGB stars and, well, it's not really a star, but supernovae. So both of them can produce dust grains. And these dust grains are formed in the circumstellar medium. That's what I call stardust. So they form dust that goes into the interstellar medium. Via the reverse shock of the supernovae, you can have also some dust destruction that can destroy a lot of the dust, 90, 95% or more, depending on various papers, sometimes less. Oops, but all this dust goes into the interstellar medium with various properties, size, and composition, depending on what you have. And you have metal accretion on the dust grains that produce some growth of the mass inside the ISM. All of this goes, of course, into molecular clouds. And via aspiration, you destroy some of the grain. So this is what we have in, let's say, the local universe. The point here is we don't understand everything, of course. This is usual. But this is at redshift mainly 0. So what happens at higher redshift? What we have, or we had so far for dust at high redshift, so you have here various papers from people maybe we don't know, Nicolas Laporte, that shows that we have a lot of dust at high redshift. This is Rebels, I think. And this is one of the big questions. How can you produce so much dust very fast? Well, this is not the topic of this, but usually dust growth is one of the assumed culprits. And well, let's assume it's a good explanation. The point is, if this hypothesis is true, we should identify a galaxy without ISM ground dust and only stardust. And we can wonder where are they. So far, we didn't have trustable stardust galaxies, and that's why and where we are very interested by JWST because it provides new information. So first, this is time, this is dust mass, and what you can see here is that supernovae start forming dust before AGB star by quite a lot. And that means that we are expecting to have first supernovae dust grains, then AGB star will produce more. But the point here is that if you want to have only stardust, you should look at the ultra-high redshift. That doesn't mean that you only have this type of dust at high redshift, but that's a more favorable place to look at. So if we come back to our life cycle of dust, it's only half of them. You start with star formation, supernovae, and you are here including dust, destruction, and formation. So this is what we are trying to identify with our data. Well, I have just one slide because you know a lot about Seagull. So that's what I used. basically, for this sample, I had NIRSPEC, NIRCam, some infrared data, and we were able to fit everything, including the line, as I mentioned before. So we get a lot of information on everything down to metallicity. So the galaxy sample, it's, well, quite fast. We had a lot of objects with NIRCam, about 1,300 NIRSPEC objects. I focused on the prism because I wanted to have a wide wavelength range, and to this redshift range with 6 AGN. So we have this redshift distribution between 4 and 8 mainly, but a few ones at higher redshift. Well, there are not many, but they are very important here, and we'll see why. So we have seen that the life cycle of dust is quite complete at low redshift. So what happens at high redshift? So we'll try to identify objects where this plays a role. So we won't look at it specifically, but we'll try to identify. And so I analyzed the previous sample to derive some parameters by fitting the spectra and the photometry. And from this, I can derive several parameters. Two of them were several of them were very important here. But here, what you see is that we have the dust attenuation in far UV and the stellar mass as a function of color-coded in redshift. So high redshift is the reddish point, and the other one are all mainly low and intermediate redshift. The first point that you can see here, that this is from Bowens et al. 2016. That's a sample of galaxy at redshift 2, 3-ish, I think. Yeah, that's what is written here. And the trend that we have between these two parameters is a bit different. We get to lower stellar mass, which is normal given that we are at higher redshifts. We have a number of AGNs here, 7, I think, that are just flagged, but nothing special about them. And we have what I called GALDAs, galaxies with an extremely low dust attenuation. And these ones are defined as follows. The dust attenuation within 2 sigma are consistent with 0. You see all these large uncertainties down. And that's the reverse Y that you see here. So all the objects in this part are what I call GALDAs. I also added this criterion, stellar mass. I'm not sure it's actually relevant now. Only this object is out of the range, but it might not be relevant. So the main one, because it's low dust attenuation, is the one on the dust attenuation, of course. So starting from this and from these objects here, so I have 49 of them out of 173. So that's quite a good sample. Just to give you an idea, from this paper here, at redshift about 1 to 2, Burat et al. Defined 3 subsamples, no infrared data, meaning UV selected, intermediate, and dusty. And all of them are here, from UV selected to the dusty one. So you see that you have quite a gap between what we have at redshift 2, 3. Redshift 0 is about the same. And all of them. Of course, that's a logarithmic scale, but still, between this one and this one, you have a factor of 20, 30, and even more below. So from this data, what we try to do is to estimate several parameters, others than the usual ones, star formation rate, etc. And I showed here a plot with dust mass versus stellar mass at redshift 0, that's the Gamma Atlas sample. You have this nice sequence here, which is from spiral galaxy. Elliptical galaxies are here. And that's what we always had observed so far. And what we want to do is to populate this area here at very low mass. Know what happens here, because these galaxies are the main stellar population, the main galaxy population, not only high redshift, but we have also some of them at low redshift. And so I tried to build the same diagram from the data I showed you before. And this is what I get. So again, redshift, stellar mass. Here we have the dust mass with the same AGN and GALDAS. I added a sample of galaxy at redshift almost 0 from Davis et al. And, well, they have this object, but they write in the paper that actually they don't know what they are. And, well, they are located in about the same region. So what do we have here? We have a trend here, which is what we observe here. That's the same one. But we have another clump sequence, I don't know, here, which is different. These are the contours of all the data points. And, well, trying to use Seagal with the mark option that you don't use, we can estimate when we can trust our dust mass. And below this value, we have only upper limits. But this is enough because you can see that even if we can estimate dust masses down to here, that's quite a large difference with the main sequence of the prime sequence that we have here. So what are these two sequences? We didn't observe that before, but many people tried to model these galaxies. And basically what we have, that's the same M dust, M star. We have two sequences. This is the ISM dust, galaxy with ISM dust mainly, grown. And this is the stardust. So you see that you have quite a large difference between the two. And what a model says that you have a transition here between 10 to the 8, 10 to the 9. But the stellar mass is not the leading parameters. Model tell you that it's just the metallicity, which is the main one. Of course, as was shown this morning by Robert, you have the mass-metallicity relation, and that's why we have the transition. So galaxy here, we remove from the stardust to the ISM dust when they reach some critical metallicity. So this is just a sketch. Let's look at true models. Wittstock et al. So this is when all the metals are into dust. And this is when you have production of dust in supernovae, 95% destroyed. And of course, if it's more, it's below. And again, we find the same difference between the two lines. Here, we don't see the transition. So I put here three models, Graziani, Mancini, Esmerian, in this redshift range. Well, redshift is changed a bit, but not. And now you see the transition from here to here. I just plot three models, but you have all a series of models that exactly show the same thing. Well, of course, you have differences because you have different input parameters, but you have a transition from here to here in approximately the same stellar mass range. But again, it's not the leading one. And when on this diagram I put my objects, you can see that they match quite well. You have the prime sequence here with ISM dust, and you have this one, which is here. That means that the supernovae are at the origin of dust here. This is the upper limit I showed you before. And well, after having worked on this, I found that one object by Fujimoto et al. Was observed with HALMA at a good mass range. It's a good metallicity. And this is an upper limit as well. So this one can qualify as GALDA, as I mentioned before, and be in this region here. So it's not the only one. That my sample is not the only one. We start to have other objects with HALMA measurements. So this is the status. So let's try to go further and interpret all of this. So, of course, GALDAs overlap a transition region from start of the galaxy to galaxy where dust grain grow by accretion. But because we have an overlap doesn't mean that it's a true answer. We should go and look into the physics itself to understand better. And I told you that the metallicity was the driving parameter. So what I did is to look at metallicity. So here you have the dust. Here you have some measurement of metallicity. And the Galdas, the galaxy with an extremely low dust attenuation, are here. And the other ones are here. And you can see that you have quite a nice difference. But, well, having the difference here is not enough. So I plotted the distribution here. Blue are Galdas, red are the other ones. And I run some statistical dust, Kolmogorov-Smirnov. And I got this value. So this shows that we can strongly reject the null hypothesis, which is both samples are coming from the same distribution. So they do come from different distribution. And the value, the threshold is about 7.6. And just to give you an idea, I plot some prediction by Jukozla et al., which is from here to here. It's quite large. Asano is here. And Fahlman is here. So this is in quite good agreement. And we find out that these are really lower metallicities than the other one. So that's the first point, which is written here again. Second one is to look at what is the link of this Galdas with the UV bright galaxies that we observe. I put redshift larger than 10, but maybe a bit below. And this is something you heard about during this school. You have here the UV luminosity function. And what was observed or predicted before was here. And what is observed is here. So you saw that you have quite a large difference. And when trying to understand what happens here, several proposals have been made. Stochastic SFH, a large star formation history with maybe some feedback free, a top EVMS, dust, and, well, IGN as well. It seems that this one can help, but is not the main and only explanation. And we'll see for the other one. So in our sample, we have galaxy from redshift 4 to 11.5. And we will see that most of the galaxies at high redshift, larger than 9, are what I call Galdas. So this is the same diagram that you saw before. At redshift larger than approximately 9, you see that most of the reddish galaxies are here. This is Mazy galaxy at redshift 11.4. And it's the same diagram, far UV, M star. And quantitatively, you get that if you are above this redshift, most of the galaxies, except one, which is very interesting, but well, that's another topic, are Galdas. When you are here, at lower redshift, you have a distribution which is approximately equal. And that means that, it disappeared, but this is about 80-something%. Oh, yes, it's here. 83%, only 23%. So when you go to redshift larger than 9, you start to see these galaxies more often, and they become dominant. Well, that was what I did. That's a paper published right now. And I tried to focus on the high redshifts, so between 8 and 14 point something now. And this is the histogram of the redshift. So you see that we have, well, actually, I think I have all the galaxies at redshift larger than 10, maybe not MUM because I didn't find the spectrum, but well, all of them, the other ones are here. And this is very interesting because when you look at exactly the same diagram, here 4 to 12, and here 8 to 14, you see that not Galdas are these blue galaxies here, these dots. So most of the not Galdas, that's the same redshift 2, 3 that we had before. And in the range here, you have only down-pointing triangles which mean upper limits. So all these galaxies, well, even these two ones, are Galdas. And you see that the one at lower redshift, except this one, are all outside the region. So this confirms what I said before. When you look at this high redshift range, most of the galaxies, if not all, are galaxies with very low dust attenuation Galdas. And this is same thing, dust attenuation versus redshift. And you see that we have quite a nice trend here with 16% of Galdas below redshift 9 and 82 above redshift 9. well, that's exactly what I said. Now, because we have lines, we can estimate metallicities, we can estimate gas mass, and that's what I did here. So I use all the galaxies, not only GALDAs. Yes, GALDAs are in blue and other ones in red. And this is the same object with ALMA data. And what you see here, stellar mass, gas fraction, is that all these galaxies have very large gas fraction, more than, let's say, 90%, maybe 95%, I don't know. And even this one, which is just on the limit, goes above. And well, this is what is expected. All the models tell you that low mass galaxies do have this type of gas mass fraction. And if you look at more models, so this is a paper from Heinz et al., this work refers to this one, you see that you have quite a nice rise here, and then the galaxies are on this range. This is 1 Zwicky 18 and S04590, which are two very, very low metallicity galaxies in the local universe. So the fact that all the galaxies are here is not unexpected. Actually, it is expected. So all objects, GALDAs and not GALDAs, have high gas mass fraction, larger than 90%. And if they still have this huge gas reservoir, that means that they also have the dust inside. I mean, it's difficult to see how you can eject or expose gas without dust. Because we are doing this data were estimated from NIRCam and NIRSPEC data, that means that we are looking really at what JWST observed, not outside. We can estimate also the density of star formations, the density of gas, and this is where GALDAs and not GALDAs are found. So that means that we have star formation efficiencies, which is a ratio of this over this, which is, well, let's say normal, maybe a bit below. These are Lyman Break galaxies at lower redshift. These are sub-millimeter galaxies. So it's about the same range, let's say. You have outliers here, which are very dusty galaxies at high redshift. So all these galaxies are very different from that. And so our total sample shows that we do not have high star formation efficiency, but normal or even a bit low. So if we come back to this diagram, so this was already, well, not rejected, but not dominant. Maximum star efficiency doesn't seem to be confirmed. Top heavy AMF can play some role, but not enough. And so the main conclusion here is that dust could be the main player here. That's because we don't have dust attenuation, to be broad, that we have this effect. Well, I forgot to say, but well, of course, the UV, absolute UV magnitude is about the same for the galaxies that I mentioned before. So let's now open it more. We have two models here by Andrea and myself here in this room. And because we are in a school, let's look at the details. We have a bit of time and see what happens. So I present this under the control of Andrea. So just to give you a summary for paper, physical origin prediction, and the origin. So if I'm not wrong, Andrea will tell us, this is not dust-free, it's attenuation-free. This is very important. We have dust moved out to kiloparsec scale by radiation pressure outflows. And the prediction is that we have extended far infrared dust halos with low surface brightness, and they should or will be observed maybe with new version of ALMA. And the main effect is because of geometry. The dust is going outside, and when you look at the galaxy inside, well, the dust column is lower, and you see dust attenuation-free galaxies. In my case, they are dust-free. Well, not really dust-free, it's very low dust attenuation. The systems are young, metal, and dust poor, stardust only, and grain growth did not start to produce grains. Spectroscopy signs from data show that we have very blue UV slope. The Balmer decrement is very near case B, and you have a lower sequence in this diagram. So the low dust mass of these galaxies is because supernovae only dust is produced and not just redistributed. You don't have dust inside or just a little bit. So, okay. The majority of metal from supernovae is retained in ASM. That's also what's said. And this puts strong constraint on the possibility of significant outflow because gas and metal should be confined to ASM. And if you have only stardust, you expect to have attenuation dust mass lower by a factor of 100 to 1,000. And this is in full agreement. But because of this, we cannot just tell it's OK. We need to check that this is enough to confirm what we see. So the main point is that the difference between extinction, which is on one rate of tight, and dust attenuation, where you have various physical parameters that produce the dust attenuation. And this is two different physical processes. And that produce something on the mass absorption coefficient, kappa, and the geometry, which are two main and crucial key elements. If you plug, for instance, Andrea's kappa value, which is the opacity, you will get something which is very, very large. And that's an important point. But this value comes from extinction on the line of sight. And when you compare to observed data, you don't have extinction, you have attenuation. You have scattering, you have mixing of star and dust, you observe different sight lines, and the opacity, the kappa, can be very different. And so these two explanations are really different, as we saw. Well, that doesn't mean that this is wrong. This is just a different approach. If you use relative transfer, this one is fully correct. If compared to normal JRC delta, this one is more correct. And so let's go to do some calculation. First, on the corner of the sprint, you can estimate the dust surface density using this value. We know the radius, we know the dust mass. We can estimate the lambda, kappa lambda using this ratio. And if it's pure foreground, you have this. If it's a mixture, you have this. And you can apply this for a given range. Let's say here, AFRUV 0.1, dust mass 10 to the fifth. Let's see what we get if you apply these values. So you doing this with galaxy of 100 parsec or 200 parsec, you get kappa values which are in this range, about 100, 200, maybe 300. And this is very different from what Andrea assumes. And now, if we look to models, Irashta, Bogarde, and Bowens, this is a paper that published a long time ago. You have different composition of dust that produce different opacities here. You can move to UV using this formula, and we get this type of values. And more specifically, you have two lines here, which is supernovae before the shock and after the reverse shock destruction. And you see the type of values that we get, depending on, well, the slope of the that we have here, which is, this is for SMC, this is for CalZT, and this is for radar 6. And when we try to put all these things into this very simple model, you can predict, depending on mixed or screen geometry, depending on kappa on this plot, and this is as a function of KV, for 100 parsec, and I have another one, 300 parsec. And what you see is that this is a region where you have galdas. You see that you have, well, very easily able to get low dust attenuation using the values that I showed before. And using all the range that I found, you also get this dust attenuation, whether at galaxies are 100 parsec or 300 parsec. This is even better. You can explain these galaxies. So everything seems to be quite simple. All is in agreement. You have the metallicity, you have the dust mass, and you have everything. And my last slide is to summarize all of this. So the main point is that these galdas contain only stardust. So you have here the dust mass. Here you have the time or mass of stellar mass. And so you start by having galaxies here forming stars. Supernova explode. So here you have a low dust mass. Then the metallicity increases. You get accretion of metals, and you have another trend. And the difference between the two explains what we saw before. And because Rosa is telling me that it's finished, that's the end. And you notice that stardust is already quite well known in different books, music, etc. Thank you.
Thank you, Denis. Do you have questions or comments? Yes, we can.
So they don't have ALMA detections?
No.
No. So how confident are you in the dust mask? I thought it was very dependent on percentage.
That's an excellent question. So basically, I assume that these objects are similar to what we have in UV-selected galaxies at redshift 4, 5, 6, 7. That's the alpine sample. And for this sample, we have quite a nice sampling of the infrared acidity. So I assume this is the same. And using this, I don't have to worry about the shape of the acidity in infrared, which is model dependent, of course, but only on how much energy there is in infrared, which is what you get from the energy balance. So I need to know how much energy is absorbed in UV. And for this, I have several parameters. First, the Balmer decrement, and then the UV slope. We have all the information for this. You can see here that the Balmer decrement is dominant one. About 80% of the dispersion is explained by the Balmer decrement, and a bit less by the UV slope. So we estimate, and we nicely estimate, you can see the difference here, how much energy is absorbed in UV, thanks to these two things in the spectrum. You have by Balmer decrement, I don't mean only H alpha, H beta, you have all the Balmer lines. And I put this in infrared. Assuming the dust distribution that I have, I get the result. If you change it, the dust temperature, you will change basically where is the dust mass, because you will have different dust mass for a different temperature. But it doesn't change the fact that you have two trends. You will get something like this. And because this is in agreement with models, that's not the true and final answer, but it seems to be reasonable. Is it okay?
Other questions or comments? Because we are running short of time. Just remember that actually the dinner is at 7:30, not at 7. So we have a bit more time. I'm saying this for the next speaker. Okay.
Maybe quarter of an hour, 15 minutes to stabilize.
Yeah, sure.
Where is it?
Oh, it's here.
Okay, sorry,
No. So I think we can start. If well, I have a question myself, but I'll ask the question.
Sure.
Because I think that you can use this kind of work otherwise.
Thank you.